Welcome to the STEM Pathways with Rohan Sharma podcast, where we dive into the exciting world of science, technology, engineering, and math. In each episode, we share exciting stories, groundbreaking research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing Felix Hermann, who is a professor at Georgia Tech. How are you doing today?
Excellent. How about yourself?
I'm doing good, and thanks for coming on the podcast. So, to get started, I wanted to ask, where'd you go for your undergrad?
I went to Delft University of Technology. So that's Delft is a town in the Netherlands. Netherlands is a tiny country in Europe, and that's the oldest engineering school in the Netherlands. So I did there both my undergraduate and my graduate work. So that included my PhD.
Yeah. So, how'd you pick your major?
So when I was at high school, this was in the 80s. So that seems a very long time ago. So it's in the 80s, right? And so the economy wasn't doing so well. So I wanted to basically train in a subject that would maximize my chances to go to the job market. And I talked to a good family friend of ours who served on the board of directors of Shell Oil Company. And he told me that engineering physics was the degree that gave you the most flexibility and left the most options open for work in STEM fields. I think the term STEM didn't exist at that time, but that was the direction he recommended. So I went and talked to people in Delft. It's only a whooping 10 miles away from where I lived. Um, and there was a professor there who was a tennis buddy of my father. I talked to him and I decided to go do engineering physics and even did a PhD with that guy after I finished my undergrad.
Yeah. So, what was your PhD research about?
So I worked in a field of, and I still work in that, of seismic imaging. So I was in a group that's called the Laboratory for Acoustics or something. So it had to do with sound, and so you can use sound to look in the human body. For instance, you can look at a baby in a mother's womb, or you can look in the earth with active seismic source. And that was traditionally to find oil and gas. Now it's more about storing CO2 underground. But that's what I did my PhD and master's in.
Yeah. So, what was your first job after completing your PhD?
So I won a fellowship from the Dutch NSF, I guess, the sort of the counterpart, to go for a year as a postdoctoral fellow to the United States. I had met at a conference a professor at Stanford at the applied math department, and I basically went there for a year with Dutch funding. And then after that, I got an offer to be a postdoc at MIT. I had also met my now wife at Stanford, so I stayed basically. So I had 1 year of funding from the Netherlands, and then I stayed as a postdoc at MIT, and then I became a professor in Vancouver some years later.
Yeah. And did your interest in your research change at all during your postdoc years?
Um, I became more realistic on. I was working on sort of difficult problems that were not necessarily easily be solved. So I became more aware of that if you want to become a professor, you need to publish papers. So I became more cognizant of that. Um, and I built a research program that's still sort of, as Frank Zappa would say, uh, conceptually continuous. So I've evolved, but over time I've broadened my research into different types of imaging, medical imaging, and I do a lot of machine learning these days. And that was certainly not there when I was a grad student or a postdoc.
Yeah. So, what'd you do in Vancouver?
So in Vancouver, I was a professor at the Earth and Atmospheric Science. No, it's called EAOS. They have all these different acronyms. Anyway, it's an Earth Sciences department at the University of British Columbia. So that's a strong school in Canada. Vancouver is a beautiful city. And so I was there for like 17 years.
And what made you make the decision of coming to Georgia Tech where you are now?
Two things. One is my wife was hired as the chair of the math department. and I felt it's good to make a change. I think Georgia Tech is academically plays, at a bit of uh, more with the big guys, right? The US, the science goes or is being conducted at a higher level. There's in principle more funding, and people are just more intense, and I like that. So it is a new challenge, which I really enjoy. Georgia Tech is a fantastic engineering school, and I'm an engineer by training, right? An engineering physicist, so I really like that. And I'm here at three departments. So I'm in EAS, still Earth Sciences, but I'm also in computational science and engineering and in electrical engineering. And that's quite unique. So I can get students from all these different schools, and that allows me to build a very diverse research group, which I thoroughly enjoy.
Yeah. And also during your 17 years at the University of British Columbia, how much did your research change then?
Um, so I started off, um, I was always a little bit theoretically inclined, so I didn't do a lot of computational work. But over time, I had very good students that helped build that up. And so we started some major software projects that are now having a real big impact in industry, because they are basically being used in production. That's one. Two, I benefited enormously from a program I attended at UCLA, and that's where basically the field of compressive sensing was born, which is a field that's now over its top. But there were at one point like 10,000 papers published in it, and that had all to do with how can you acquire data more efficiently using sort of randomized techniques, and that had an enormous impact on my research program. And so that was back in 2004, but I kept doing that stuff until basically 2015 or 16. So that had at least more than a decade a big impact on my research program. So if you are a young professor somewhere, you can participate in these longer term programs that run at some of these mathematics institutes or machine or computer science institutes. That's really a very good way to embark on new research directions.
Yeah. So, do you think being a professor has changed a lot from maybe like 20, 30 years ago to someone who's trying to become a professor today?
Yeah, I don't envy you guys. So there are two things, right? So one is when I was young, I had to take my bike and go to the library and do a search for a publication, and then I had to order that, and then maybe some copies, uh, paper copies would come 2 or 3 weeks later, right? Whereas now you type everything in Google, and now you do everything in ChatGTP, so you have instantaneously access to information. So that makes you, on the one hand, much more efficient. On the other hand, the expectations and the productivity of young faculty are much larger, much higher. So they work at a much higher rate than we ever did when I was young. And so, in that sense, the competition is very high, and people work at a very high production rate. And I don't envy. So let me put it that way: if I were to be a young professor now, I wouldn't know whether I would be as successful as I have been. Having said that, the tools, the fact that I am now working in machine learning is only because it really allows me to do things that people were thinking about theoretically back 20, even 10 years ago and could never do. And now you can do that, in particular using techniques from generative AI, right? So that really allows you to come up with new formulations of the type of problems you're interested in that you could never do before. And so, in that sense, the new guys are lucky.
Yeah. So, back to Georgia Tech, you're kind of talking about how you think it ranks like kind of among with the highest players in the game when it comes to STEM and engineering.
Sure, sure.
What do you think makes it stand out?
It's an honestly engineering school, right? So UBC had a medical school, and all the money went to the medical school, and engineering was sort of seen as second, lower level. Georgia Tech is truly a engineering school. They also fully embraced machine learning across the board, so it's everywhere. Mathematics is everywhere, right? So the students at Georgia Tech don't shy away from learning the hardcore mathematical and statistical principles that you need to be successful. That's not always true at other places. That really sets Georgia Tech apart. Also, the students, you can give them really tough assignments and they just soldier through. I also had the privilege to work a lot in capstone courses, in particular Create X, which is a capstone undergraduate course where students are basically trained to put a company together in teams. And in a very short time span of a term, they come up with the idea and with prototypes. And I was really impressed at how fast the students can actually solve problems and actually come up with a concrete implementation of the idea.
Yeah. And then from a research perspective, do you think it's also do you think the undergrad varies a lot from the graduate program?
Yes, because a graduate program, and this is where I think the US is much stronger than most places in the rest of the world. So I think undergraduate, except maybe for the top schools, where I did my undergraduate work can easily compete. But where the real stuff happens is at the graduate school, particular PhD, where students are trained to do independent research. And there I see that the level of the graduate students I've been producing here and at UBC, and if I compare myself with the Netherlands, I think that's where the US really excels. But that calls for very hard work, long days, and ownership of the problem that you work on, and finding a good balance to be trained in the beginning by taking some classes, but then develop your own independent research program.
Yeah. So what are your future goals with being a professor?
Well, so I work now in this field where we try to store massive amounts of CO2 underground. And so that is to offset the impact of the fossil fuel industry that produced a lot of CO2, right? So if you take the CO2 out of the atmosphere, we can help mitigate the effects of climate change. And so I want to make that technology available to everybody in the world. So everything I do is open source, no secrets, no patents. And I really hope to, in the remaining years I have, to accelerate innovation in that area so that it can at least help us mitigate some of the effects of climate change and sort of undo the bad we have done over the last 30 or 40 years by using fossil fuels. And I was part of the problem, so now I plan to be a part of the solution. I also would like to apply my techniques in medical imaging, and we have had some successes, but it's challenging to find funding for it. But I'm still pretty keen to continue working on that too.
And the research you're doing right now, is it mostly like just you kind of leading at Georgia Tech, or are you working with professors or faculty at other universities?
I work around the world. I work with people, for instance, at the Imperial College London. We built that software tool, the Vito, that's now run by industry that allows you to solve really large scale wave equations. Super cool. It is something where you write down the wave equation and it spits out automatic super optimized code. And that's now used in production on hundreds of thousands of cores by industry. We have other collaborations with people in Norway where we look at how fluid flows in the earth, because if you inject CO2, that excess of fluid, and we need to understand that. And I have collaborations across the US as well. And that's important as a professor to have connections and collaborate.
Is that also one of the massive changes that's happened now compared to like 20 years ago? Is that the ease of communication also makes everything way more efficient?
Of course. And the fact that there are things like GitHub, right? That didn't exist when I was a graduate student. Most people that would work with oil industry would have proprietary codes they won't share. So nowadays, there's this whole new model of open source and also reproduction of research results, right? Where you can take somebody's results and then reproduce them or apply their algorithm to your own data. And in that sense, the developments go exponentially faster than they used to. Thanks to availability of data, availability of compute, availability of code that other people have produced, availability of benchmarks that you can compare. So these things and I'm not the only one who says this. Also, a professor I know at Stanford, David Donahoe, has been writing about this, but that has resulted in much faster, development of technology. Look at machine learning, right? 5 years ago and now, that's an enormous jump. And so some people claim we are close to the singularity where things go exponentially fast. And so that's pretty cool to be part of that. Um, but yeah, I don't envy you guys if you start with that. I have no idea where, if you were at my stage of your career, where the world is then. If it continues like this, it will be really fast, right? So,
Yeah. So for my last question, I wanted to ask if you have one piece of advice for someone who's still in high school or early in college wanting to follow a similar career path as you.
okay, so rule number one, do what you like to do. Because if you do what you like to do, you're really good at it. Two, don't be afraid of, or don't listen to what other people think you should be doing. Choose your own path. But try to do something that's different than others and try to do something that's not easy. So the reason I chose engineering physics was because it was perceived as the most difficult study at the university I was. And because with that, you create options, right? Because you have then you're basically you have a leg over to the competition who in my days, people that were lazy went to go and study law, right? Because that was easy. Whereas engineering physics was more difficult. And so do that. With STEM, you have more options. And then choose something that you're good at, and then you have most options. Don't do what you that other people tell you what you should do. So, for instance, I don't work on machine learning that has to do with, say, categorizing YouTube videos. I work machine learning in seismic imaging, which is not a huge field, but it's much more interesting and it's a lot of fun. So find the niche or the subject that you like and follow that.
All right, then. Thank you for joining me on the podcast today.
Sure, it was my pleasure. Thank you. Bye bye.